NASA just changed the numbers, not updated them, not refined them, but fundamentally revised the trajectory calculations for 3I Atlas in ways that eliminate the most extraordinary coincidence ever documented in planetary science. And they did it quietly, without announcement, without explanation, within days of Harvard astrophysicist Avi Loeb publishing calculations showing that the interstellar visitor is headed toward Jupiter with precision that defies natural explanation. The original data, compiled from observations at 230 observatories worldwide, predicted 3I Atlas would pass within 53.445 million kilometers of Jupiter on March 16, 2026. That's not just close to Jupiter's Hill radius, the gravitational boundary where Jupiter's pull dominates over the Sun. It's identical to the Hill radius within measurement error, a 1 in 26,000 coincidence across Jupiter's orbital path. And here's what makes this impossible to dismiss as chance. The match required non-gravitational acceleration, a course correction during perihelion when the object was hidden behind the Sun, unreachable by Earth-based telescopes, accelerating by precisely the amount needed to shift its trajectory by 0.1 million kilometers and landed exactly at the Hill radius boundary. Then Loeb emailed NASA, and within 48 hours, the forecasted perigove distance changed. The acceleration model changed, and suddenly 3I Atlas is now predicted to pass slightly outside the Hill radius instead of precisely on it. If this is making your head spin, if you're wondering whether we're watching real-time suppression of evidence that 3I Atlas might be technological, make sure you subscribe and hit like right now. Drop a comment with where in the world you're watching from, and whether you think NASA's revisions are legitimate refinement or something more deliberate. Because what we're about to uncover goes beyond trajectory calculations. It's about how science responds when data points toward conclusions that institutions aren't ready to accept. And March 16, 2026 will provide the verdict, regardless of what models predict today. Let's start with what the Hill radius actually means, and why arriving precisely at that boundary suggests intent rather than accident. The Hill radius, named after American astronomer George William Hill, defines the region around a planet where its gravitational influence exceeds the Sun's tidal forces. For Jupiter, the largest planet in our solar system, with a mass 318 times Earth's, this radius extends roughly 53 million kilometers from its center when Jupiter sits at its current distance from the Sun. Interior to that boundary, Jupiter can capture and hold satellites. Objects placed just inside the Hill sphere orbit Jupiter stably without being pulled away by solar gravity. The Lagrange points L1 and L2, positions of gravitational equilibrium where forces from Jupiter and the Sun balance perfectly, sit precisely on the Hill radius. And those points are ideal for parking satellites, because they require minimal fuel for orbital corrections. Objects at L1 and L2 maintain their positions with tiny adjustments, making them energy-efficient locations for long-term operations. Now here's the key insight. If you were designing a probe to study Jupiter, if you wanted to deploy instruments that could orbit the gas giant without constant propulsion, where would you release them? Exactly at the Hill radius. Release them inside, and they orbit Jupiter. Release them outside, and the Sun's gravity drags them away. The Hill boundary is the perfect deployment altitude for maximum operational efficiency with minimum fuel expenditure. And according to NASA's JPL Horizon system, based on observations from 230 ground-based observatories tracking 3I Atlas's position against background stars over 5 months, the object was on course to arrive at precisely that distance. Not 50 million kilometers, not 60 million, exactly 53.445 million kilometers, matching the Hill radius of 53.502 million kilometers, to within 1 standard deviation of measurement uncertainty. The probability of this occurring by chance is calculable. Jupiter's orbital path around the Sun traces a circle roughly 4.9 billion kilometers in circumference. The Hill radius represents a target zone about 100,000 kilometers wide when accounting for measurement uncertainty. The ratio gives you the probability. Divide 100,000 by 4.9 billion. The result is approximately 0.00002, or 1 chance in 50,000. But that calculation assumes the match happened purely through the object's original interstellar trajectory, the path it was on when it entered our solar system back in July. And that's where the story becomes genuinely unsettling, because 3I Atlas didn't arrive at the Hill radius through its original trajectory. It arrived there through course correction. Between October 29th and early November, when 3I Atlas passed perihelion at 130 million miles from the Sun, instruments detected non-gravitational acceleration. The object was not following a purely gravitational path determined by the Sun and planets. It was accelerating, pushed by forces beyond gravity. For natural comets, this acceleration comes from asymmetric venting, jets of sublimating gas erupting preferentially from one side of the nucleus, creating thrust through the rocket effect. Momentum conservation requires the nucleus to accelerate opposite to the jet direction. But here's the critical detail. The magnitude of that acceleration, measured at approximately 5 times 10 to the minus 7 astronomical units per day squared, shifted 3I Atlas's trajectory by exactly the amount needed to bring its perigove distance from wherever it would have gone naturally down to the Hill radius value. Let me state that more clearly. Without non-gravitational acceleration, 3I Atlas would have missed the Hill radius. With acceleration of slightly different magnitude, it would also miss the observed acceleration occurring when and where it did, behind the Sun at perihelion, where no telescopes could observe directly, corrected the trajectory with precision that landed the object exactly where it needed to be to deploy hardware at Jupiter. This is not speculation. This is what the numbers said before NASA revised them. On October 30th, 2025, JPL Horizons listed the radial acceleration component, a 1, normalized at Earth-Sun distance, as 1.6 times 10 to the minus 6 astronomical units per day squared. That value, combined with observations of the object's position over time, produced the perigove forecast of 53.445 million kilometers. Then came Loeb's analysis. He calculated the Hill radius independently using the standard formula, determined it matched the forecast distance within error bars, and published his findings in a Medium article titled An Extraordinary New Anomaly of 3I Atlas. The article explained the implications. If the match is real, if 3I Atlas genuinely arrives at the Hill radius in March, then the coincidence becomes the most statistically significant anomaly in a growing list of improbabilities surrounding this object. And if the match required course correction, if non-gravitational acceleration precisely tuned the trajectory, then natural explanations become untenable. Comets don't navigate. Spacecraft do. Loeb emailed his analysis to Davide Farnocchia, the JPL scientist responsible for maintaining the Horizons ephemeris data. The email explained the coincidence, showed the calculations, and asked whether JPL had considered this implication. There was no response. But within days, the A1 value on the Horizons website changed. First, it dropped by a factor of 4 to 4 times 10 to the minus 7. Then it dropped again by a factor of 6 to 6.8 times 10 to the minus 8. And accompanying the revision was a change in the model used to calculate non-gravitational effects. The original model assumed water ice sublimation, using radial dependence appropriate for H2O vaporizing as the comet heats. The new model assumes carbon dioxide sublimation, using a 1/r² dependence suitable for CO2 ice. That change matters because CO2 sublimates at greater distances from the sun than water, contributing acceleration from farther out where observations are more complete, reducing reliance on unmeasured activity during perihelion. The result of these revisions? The new forecast for perigove distance is 53.587 million kilometers, just outside the Hill radius by about 85,000 kilometers. The coincidence disappears, the match no longer holds. And the most extraordinary anomaly of 3I Atlas, the one suggesting deliberate navigation toward a target optimized for satellite deployment, gets explained away as modeling error. NASA's official position, though never explicitly stated, becomes clear through the revision itself. The original match was artifact, not evidence. The trajectory never actually aligned with the Hill radius. It only appeared to because the wrong sublimation model was applied. But there's a problem with that explanation. Multiple problems, actually, all pointing toward the revised model being inadequate and the original forecast being closer to reality. Let's examine the evidence systematically, starting with what observations tell us about 3I Atlas's brightness evolution near perihelion. When comets approach the sun, they brighten as sublimation increases, releasing more gas and dust that scatters sunlight. The brightness curve, luminosity as a function of heliocentric distance, reveals how rapidly the comet activates. For typical comets sublimating water ice, brightness scales as 1 distance to a power between 2 and 4, depending on how distributed the active regions are across the surface. For carbon dioxide ice, which sublimates at lower temperatures, the relationship is shallower, 1/distance squared, because CO2 activity begins farther from the sun and ramps up more gradually. Observations of 3I Atlas show it brightened steeply near perihelion, far more steeply than a 1/r² model predicts. Analysis by Qicheng Zhang and Carl Battams, published in preprint before NASA's revisions, found a brightness profile scaling as 1/r to the power of 7.5 inside 2 astronomical units. That's an extremely steep dependence, indicating the comet activated suddenly and intensely as it approached the sun, consistent with water ice beginning to sublimate in concentrated regions on the surface. A separate analysis by Marshall Eubanks and collaborators confirmed the steep profile, showing luminosity evolution dominated by coma brightness, which reflects mass loss if scattered sunlight is proportional to the amount of material released. If the brightness scales as 1/r to the 7.5 power, then the non-gravitational acceleration, which depends on mass loss rate, should scale similarly. More mass loss means more thrust. The relationship is direct, but NASA's revised model uses 1/r², a much shallower dependence that spreads the acceleration over larger heliocentric distances and reduces the contribution from perihelion, the period when brightness observations indicate activity was highest. This mismatch between observed brightness evolution and modeled acceleration profile suggests the revised JPL model is not capturing the true physics. It's fitting a curve to match observations at large distances while underestimating what happened near perihelion. Why does this matter? Because the perihelion phase is when 3I Atlas was hidden behind the sun, unobservable from Earth. Telescopes couldn't track it directly during October while it swung around the sun at closest approach. The object went behind the sun in late September, emerging in early November. During that gap, all we have is inference, models that predict what should have happened based on physics. And if the model underestimates perihelion activity, if it assumes gentle CO2 sublimation when the reality was violent water ice venting, then the calculated trajectory becomes unreliable. The course correction that occurred during that hidden period, the non-gravitational acceleration that shifted 3I Atlas onto its current path, remains unmeasured directly, estimated only through its effects on the orbit as determined from pre- and post-perihelion positions. Here's the uncomfortable implication. If you wanted to hide a course correction, if you wanted to maneuver without being observed directly, the optimal time is perihelion when the target is behind the Sun. Earth-based telescopes can't see through the Sun. Spacecraft in solar orbit might catch glimpses from different angles, and NASA's SOHO observatory did image 3I Atlas during perihelion using its coronagraph, but resolution was limited, and details of jet activity were obscured by the Sun's glare. Whatever happened during that period, whatever thrust events altered the trajectory, occurred in a blind spot where direct measurement was impossible. We only know acceleration happened because the post-perihelion orbit doesn't match the pre-perihelion projection. Something pushed 3I Atlas, and the magnitude of that push was exactly what was needed to place the object on course for Jupiter's Hill radius. Now, Loeb's email to JPL highlighted this coincidence, and within days, the model changed in ways that eliminate the match. Is that legitimate scientific refinement, incorporating better understanding of the object's composition and sublimation physics? Or is it motivated reasoning, adjusting parameters to avoid a conclusion that challenges naturalistic assumptions? The answer depends on whether the revised model better fits all available observations or only selectively fits some while ignoring others. Let's test the model against what we know. The Hubble Space Telescope imaged 3I Atlas on July 21, 2025, when the object was 277 million miles from Earth at a heliocentric distance of approximately 2.4 astronomical units. The image showed a compact nucleus surrounded by a diffuse coma with faint elongation, suggesting a developing tail or antitail structure. Analysis of that image, discussed in Loeb's earlier publications, indicated the coma was dominated by scattered sunlight from dust and gas, with brightness consistent with significant mass loss even at that distance. If CO2 sublimation were the primary driver, activity at 2.4 AU should be minimal because carbon dioxide ice doesn't sublimate efficiently beyond about 3 AU. Yet the Hubble image shows clear coma structure, suggesting volatiles more active than CO2 were already venting. Fast forward to November. Post-perihelion. Images from amateur astronomers show 3I Atlas with enormous jet structures extending millions of kilometers in multiple directions, including the now famous antitail pointing toward the Sun and the even larger tail streaming away. These jets, visible in photographs from Mitsunori Tsumura, Peter Carson-Lay, Elena Walter, and others, represent sustained mass loss at rates calculated by Loeb to exceed billions of tons over 2 months. For CO2 ice to produce those jets, through natural sublimation, the nucleus would need exposed surface area far exceeding what Hubble observations of the compact nucleus allow. The energy budget doesn't close. The observed activity is too intense for the assumed composition. But if the dominant volatile is water ice, which sublimates far more aggressively inside 2 AU and produces higher gas velocities due to its lower molecular weight, then the observed jets make sense. Water ice heated to temperatures reached near perihelion at 1.36 AU produces thermal velocities around 600 meters per second for H2O molecules versus 400 meters per second for CO2. Higher velocity means greater thrust for the same mass loss, or equivalently, less mass loss needed to produce observed acceleration. And if water sublimation dominated near perihelion, then the radial dependence should be steep, matching the observed brightness profile of 1/r to the 7.5 power, not the shallow 1/r squared that NASA's revised model assumes. So why did JPL switch from a water-based model to a CO2-based model? The official documentation, available on the Horizons website, references work by Brian Marsden and collaborators establishing standard models for cometary non-gravitational forces. Marsden's models use different radial dependencies depending on which volatile dominates. Water models are steeper. CO2 models are shallower. Selecting between them requires evidence about composition, typically obtained through spectroscopy, measuring emission lines from the coma. For 3I Atlas, spectroscopic data from multiple observatories has detected both water and carbon dioxide, along with carbon monoxide and various organic molecules. The relative abundances indicate a mix, not pure CO2. Given mixed composition, which model should JPL use? The answer should be whichever model best fits the observed brightness curve and the measured deviations from gravitational trajectory. And by that standard, the steep, water-based model fits better than the shallow CO2 model. The brightness data supports steep dependence. The observed jet activity supports intense perihelion venting. The original forecast using the water model, which placed 3I Atlas at the Hill radius, was consistent with those observations. The revised forecast using the CO2 model is not. It underestimates perihelion activity, spreads acceleration over larger distances, and produces a perigove distance that conveniently avoids the Hill radius coincidence by just enough to be dismissible as near miss rather than direct hit. This looks like fitting the data to avoid an uncomfortable conclusion. And if that's what's happening, if institutional pressure or scientific conservatism is driving model selection rather than observational evidence, then we're witnessing something troubling. Science is supposed to follow the data wherever it leads, even toward conclusions that challenge paradigms. But in practice, scientific institutions are conservative, resistant to extraordinary claims, biased toward conventional explanations, even when conventional explanations require more assumptions and fit the data less well than alternatives. The extraordinary claim here is that 3I Atlas is navigating, that it used course correction during perihelion to place itself on trajectory for Jupiter's Hill radius, and that it did so with precision suggesting intelligent control. The conventional claim is that all observed behavior results from natural sublimation, that the Hill radius match is coincidence or modeling artifact, and that revising acceleration models eliminates the anomaly. Institutions prefer the conventional claim because accepting the extraordinary claim opens doors that most scientists aren't ready to walk through. If 3I Atlas is technological, if it's a probe sent by extraterrestrial intelligence, then the implications cascade into every domain of human knowledge. We're not alone. Intelligence exists elsewhere. Civilizations capable of interstellar travel are visiting our solar system, and everything we thought we understood about the galaxy's emptiness and the rarity of intelligence requires re-evaluation. That's a paradigm shift, a Copernican revolution in reverse, where Earth goes from being unremarkable in a populated cosmos to being under active observation by advanced civilizations. Scientists resist paradigm shifts, not because they're closed-minded, but because paradigms are useful. They provide frameworks for interpreting data, for designing experiments, for educating new generations. Abandoning a paradigm is costly. It requires rewriting textbooks, retraining intuitions, discarding decades of work built on assumptions that no longer hold. So institutions demand extraordinary evidence before accepting extraordinary claims. And extraordinary is subjective, defined by the paradigm being challenged. In this case, the paradigm is that comets are natural objects, icy debris left over from planetary formation, occasionally perturbed into orbits that bring them near the sun where solar heating drives activity. Interstellar comets are rare but expected, ejected from other stellar systems by gravitational interactions, wandering the galaxy until chance brings them near our sun. Anomalous behavior, like Oumuamua's non-gravitational acceleration, or 3I Atlas's improbably precise trajectory toward Jupiter should be explained through increasingly exotic natural mechanisms: nitrogen, ice, hydrogen icebergs, unusual sublimation physics, before considering the possibility that some interstellar visitors might be technological. But what if the paradigm is wrong? What if interstellar visitors include both natural objects and technological ones, with the latter specifically targeted toward solar systems showing signs of habitability or technological activity? Then the prior probability for technological origin shifts dramatically. Instead of requiring overwhelming evidence to overcome the assumption that intelligence is rare and interstellar travel impossible, we'd require only moderate evidence, consistent with what we'd expect from reconnaissance probes designed to blend in with natural objects while conducting surveys of planetary systems. And 3I Atlas fits that profile perfectly. It resembles a comet enough to avoid immediate detection as artificial. It displays jets and coma consistent with sublimation, but it also shows anomalies: the anti-tail, the collimation, the mass loss without fragmentation, the trajectory precision, that push natural explanations to breaking points while being straightforwardly explicable if the object employs technology. The Hill radius coincidence is the strongest anomaly yet, a 1 in 26,000 statistical improbability, enabled by course correction during the only period when Earth-based observation was impossible, placing the object exactly where you'd expect if its mission involves deploying satellites around Jupiter. And NASA's response to that coincidence, revising the acceleration model to eliminate the match, raises questions about whether the revision is scientifically justified or institutionally motivated. We'll have the answer in March, regardless of what models predict today, regardless of which sublimation physics JPL assumes. The actual trajectory is determined by the object's physical properties and the laws of orbital mechanics. On March 16, 2026, 3I Atlas will pass Jupiter at whatever distance its true path dictates. Spacecraft in the Jovian system, including NASA's Juno orbiter and ESA's JUICE mission currently en route, will observe the encounter. If 3I Atlas passes within the Hill radius as the original JPL forecast predicted, then the coincidence is real, and Loeb's hypothesis gains credibility. If it passes outside the Hill radius as the revised forecast predicts, then the CO2 sublimation model is vindicated and the match was indeed artifact. But there's a third possibility, more intriguing and more unsettling than either confirmation or refutation. What if 3I Atlas maneuvers again between now and March? What if the course corrections we've seen are not one-time events, but ongoing adjustments, active navigation that continuously updates the trajectory to compensate for gravitational perturbations and maintain the desired approach geometry? Natural comets don't do this. They vent asymmetrically based on which parts of the surface face the sun, producing thrust that varies with rotation and heliocentric distance, but doesn't respond to navigation requirements. Technological objects, by contrast, can fire thrusters as needed, making course corrections timed to achieve specific orbital goals. If 3I Atlas makes additional maneuvers, if observations between December and March show trajectory deviations inconsistent with passive sublimation, then the technological hypothesis becomes unavoidable. You can explain one bout of non-gravitational acceleration through natural means. You can explain two if you stretch the physics, but sustained, repeated corrections that continuously refine the trajectory toward a specific target altitude at a specific time. That's navigation, that's control, and that forces acknowledgement that we're dealing with intelligence. The December 19th Earth flyby provides a critical observation opportunity before the Jupiter encounter. When 3I Atlas passes within 269 million kilometers of Earth, every major telescope will point toward it. Hubble and Webb will resolve surface details. Ground-based spectroscopy will measure jet velocities and chemical compositions. Astrometry will track position with precision sufficient to detect tiny trajectory variations. If the object maneuvers during or after the Earth encounter, if it adjusts its path in response to gravitational perturbation from Earth's mass, we'll see it. The data will be unambiguous, and the implications will be inescapable. This is why the coming months matter so profoundly. We're not just watching a comet. We're watching a test case for how science responds to anomalies that challenge fundamental assumptions about our cosmic solitude. If institutions respond by following the evidence, by acknowledging when observations point toward uncomfortable conclusions, then science demonstrates its strength, its commitment to truth over comfort. But if institutions respond by adjusting models to eliminate anomalies, by preferring explanations that preserve paradigms over explanations that fit data, then we're witnessing something darker: the subordination of science to institutional inertia, the protection of worldviews at the expense of discovery. Loeb has been vocal about this dynamic throughout his career. His advocacy for taking Oumuamua's technological possibility seriously, his willingness to propose that 3I Atlas might be a mothership seeding Jupiter with hardware, these are not reckless speculation. They're applications of Bayesian reasoning, updating probabilities based on observed evidence rather than clinging to prior assumptions regardless of data. And he's been criticized for it, accused of attention-seeking, of lowering scientific standards, of encouraging sensationalism. But the critics misunderstand the core issue. The question is not whether Loeb's specific hypotheses are correct. The question is whether they're scientifically legitimate, whether exploring technological explanations when natural explanations require increasingly exotic assumptions is valid scientific inquiry or forbidden speculation. History provides guidance. Every major scientific revolution, heliocentrism, evolution, relativity, quantum mechanics, faced fierce resistance from establishments invested in prevailing paradigms. Galileo was forced to recant heliocentrism. Darwin delayed publishing for decades, knowing the reaction his theory would provoke. Einstein's relativity was dismissed as mathematical abstraction until experiments confirmed it. Quantum mechanics was rejected by Einstein himself because it violated his intuitions about how nature should work. In each case, the revolutionary idea eventually prevailed, not because institutions suddenly became open-minded, but because accumulating evidence made the old paradigm untenable, forcing grudging acceptance despite institutional resistance. We may be entering a similar period now, watching the early stages of a paradigm shift that future generations will study as pivotal to humanity's understanding of its place in the cosmos. Or we may be watching a false alarm, anomalies that ultimately get explained through conventional physics, leaving the paradigm intact and teaching lessons about the importance of skepticism. We don't know yet. The evidence is ambiguous, suggestive but not conclusive, intriguing but not definitive. And that's exactly when scientific integrity matters most, when data could go either way and the choice of models and interpretations determines which conclusions seem reasonable. NASA's revision of the 3I Atlas acceleration model is a choice. It's a choice to apply CO2 physics instead of water physics. It's a choice to spread acceleration over larger distances instead of concentrating it at perihelion. It's a choice that eliminates the Hill radius coincidence. And choices reveal values. Does the institution value finding truth regardless of implications, or does it value preserving frameworks regardless of fit? The answer emerges through actions, through which models get used, which data gets emphasized, which anomalies get investigated versus dismissed. March 16th will force clarity. The object will arrive at Jupiter, the distance will be measured, and one of three outcomes will manifest. The perigove distance matches the Hill radius. confirming the extraordinary coincidence and demanding serious consideration of technological navigation. The perigove distance misses the Hill radius by the amount the revised model predicts, validating NASA's CO2 sublimation assumption and relegating the original match to modeling artifact. Or the perigove distance lands somewhere between, suggesting neither model fully captures the physics, leaving ambiguity intact and debate ongoing. But there's also the possibility of definitive resolution through something more direct than trajectory precision. If 3I Atlas releases objects during the Jupiter encounter, if spacecraft like Juno detect new satellites appearing in Jovian orbit after the flyby, then speculation transforms into fact. We'll have confirmation that the interstellar visitor carried payloads, that it deployed hardware, that intelligence is operating in our solar system. The Hill radius targeting becomes explicable not as coincidence, but as optimal deployment geometry. The course corrections become navigation, and humanity faces the reality that we are not alone, that we are being observed, and that the observers possess capabilities beyond anything we can currently achieve. That possibility, remote as it may seem to those conditioned by paradigms that dismiss technological explanations reflexively, deserves investigation proportional to its significance. Even if the probability is small, even if most scientists believe natural explanations will ultimately suffice, the implications of the technological alternative are so profound that ignoring it constitutes negligence. This is Pascal's wager applied to astrobiology. If we investigate and find nothing, we've spent resources exploring a hypothesis that proved false, but advanced our understanding of cometary physics in the process. If we dismiss investigation and miss genuine evidence of extraterrestrial intelligence, we've failed in the most consequential scientific opportunity in human history. Loeb understands this asymmetry. That's why he continues highlighting anomalies despite professional cost. That's why he published the Hill radius calculation, knowing it would invite ridicule from colleagues who prefer conservative interpretations. And that's why he's now pointing out that NASA's model revisions may be inadequate, that the brightness data suggests steeper radial dependence than CO2 physics allows, that the original forecast might have been more accurate than the revision. He's not backing down. He's doubling down on the importance of following evidence, even when evidence points toward uncomfortable territories. The coming months will test whether the scientific community can rise to that standard. Can we observe 3I Atlas with genuine openness to any conclusion the data supports? Can we analyze the Jupiter encounter without predetermined frameworks that dictate acceptable versus unacceptable interpretations? Can we acknowledge if the Hill radius match materializes that it constitutes significant evidence for technological control? Or will we construct increasingly elaborate natural explanations, adjusting models until any coincidence can be explained away, preserving the comfortable belief that comets are just comets and interstellar visitors are just random debris? The answer to those questions will define this era of astronomy. Either we're living through the transition from assumption of cosmic solitude to recognition of cosmic community, or we're living through another chapter in the long history of false alarms and misinterpreted anomalies. But we can't determine which, without honest investigation, without willingness to consider possibilities that challenge comfortable paradigms, without commitment to following evidence wherever it leads, even if the destination is somewhere we never expected to go. Welcome to the Sleepy Observer. Thank you for engaging with these questions, for thinking critically about what the data means, for refusing to accept easy answers when the observations demand deeper analysis. This channel exists to explore the boundaries of our knowledge, to examine the mysteries that mainstream science sometimes overlooks or dismisses, to ask whether we're truly alone, or whether the evidence has been pointing toward company all along and we've been too conditioned by paradigms to see it. Subscribe so you don't miss what happens in March. Comment with your thoughts on whether NASA's revisions are legitimate or suspicious. And remember that we're all watching this unfold together, trying to make sense of a universe that refuses to stay predictable. Good night, and clear skies. Part 1. Understanding the Hill sphere and why it matters for satellite deployment. To fully appreciate why 3I Atlas, arriving precisely at Jupiter's Hill radius, is extraordinary, we need to understand the physics governing gravitational spheres of influence, and why that particular boundary is optimal for deploying orbital hardware. The concept traces back to the restricted three-body problem, one of the oldest unsolved challenges in classical mechanics. When you have three massive objects, the Sun, a planet, and a much smaller third body like a satellite or asteroid, their mutual gravitational interactions create regions of space where different forces dominate. Close to the planet's gravity is strongest. Far from the planet, the Sun's gravity dominates. And at intermediate distances, there's a transition zone where both gravitational pulls are comparable, and the Sun's tidal forces start ripping objects away from planetary orbit. The Hill sphere, also called the Roche sphere, though technically that term refers to a slightly different concept, defines that transition boundary mathematically. The formula is straightforward. Take the distance between the planet and the Sun, multiply by the cube root of the planet's mass divided by 3 times the Sun's mass. For Jupiter on March 16, 2026, when it will be located 783.8 million kilometers from the Sun, the calculation proceeds as follows. Jupiter's mass is 1.89, 8 times 10 to the 27th kilograms. The Sun's mass is 1.989 times 10 to the 30th kilograms. Divide Jupiter's mass by 3 times the Sun's mass, take the cube root, and you get approximately 0.06826. Multiply that by Jupiter's solar distance of 783.8 million kilometers, and the Hill radius comes out to 53.502 million kilometers. That's not approximate. That's the actual calculated value, using the standard three-body physics that has governed orbital mechanics since the 1800s, when George William Hill first derived these relationships while studying lunar motion. The number 53.502 million kilometers represents the maximum distance from Jupiter, where an object moving slowly, relative to the planet, can maintain a stable orbit without the Sun's gravity pulling it away. Inside that radius, Jupiter wins the gravitational tug-of-war. Outside that radius, the Sun wins. And right on the boundary, at exactly 53.502 million kilometers from Jupiter's center, you find the L1 and L2 Lagrange points, positions where gravitational forces from Jupiter and the Sun balance the centrifugal force experienced in the rotating reference frame. Lagrange points are gravitational sweet spots, discovered by mathematician Joseph Louis Lagrange in the 1770 seconds while studying the Earth-Moon system. There are 5 such points in any two-body system. L1 lies between the two masses. L2 sits on the far side of the smaller mass. L3 is opposite L2 on the far side of the larger mass, and L4 and L5 sit 60 degrees ahead and behind the smaller mass in its orbit. For Jupiter, the L1 point is located sunward of the planet at the Hill radius. The L2 point is located anti-sunward also at the Hill radius. And both positions are ideal for parking satellites because objects placed there experience near zero net force. They neither fall toward Jupiter nor drift away toward the Sun. They hover, maintaining position with minimal fuel expenditure. This is why human spacecraft use Lagrange points extensively. The James Webb Space Telescope orbits the Earth-Sun L2 point, sitting 1.5 million kilometers from Earth, on the opposite side from the Sun, maintaining that position with tiny thruster corrections every few weeks. The Solar and Heliospheric Observatory, SOHO, sits at the Earth-Sun L1 point between Earth and the Sun, continuously observing solar activity without being blocked by Earth's bulk. Both missions exploit the fuel efficiency of Lagrange point orbits, achieving stable configurations that would require constant thrusting at other locations. Now apply this to 3I Atlas. If the object is a mothership designed to seed Jupiter with technological devices, where would you release them for maximum operational longevity with minimum fuel requirements? Exactly at the Hill radius, precisely at the L1 or L2 Lagrange points. Release hardware there, and it orbits Jupiter stably, held by the planet's gravity, but not requiring constant propulsion to maintain position. Release hardware inside the Hill sphere but away from the Lagrange points, and it eventually settles into stable orbit around Jupiter through gravitational dynamics, but the settling process takes time and burns fuel. Release hardware outside the Hill sphere, and the Sun's gravity drags it away, requiring continuous thrust to maintain proximity to Jupiter. The Hill radius is optimal, and JPL's original forecast, calculated from observations at 230 observatories over 5 months, predicted 3I Atlas would arrive at exactly that distance, exactly, within measurement error of 60,000 kilometers across a target zone 53 million kilometers from Jupiter. The probability of that match occurring accidentally is tiny. Jupiter's orbital circumference is approximately 4.9 billion kilometers. The Hill radius represents a target window about 100,000 kilometers wide when accounting for observational uncertainty. The ratio, 100,000 divided by 4.9 billion, gives roughly 1 chance in 49,000. But that assumes the match happened through the object's original interstellar trajectory, the path it was on when it entered the solar system back in July, with no subsequent alterations. And that's provably not what occurred. The object underwent non-gravitational acceleration during perihelion, measurable through astrometric position data, showing deviations from purely gravitational motion. That acceleration shifted the trajectory, and the magnitude of the shift, approximately 0.1 million kilometers in peri-Jove distance, was precisely what was needed to move the flyby point from wherever it would have naturally gone down to the Hill radius value. This is where coincidence becomes implausible. Not only does the final distance match the Hill radius, but the course correction required to achieve that match occurred exactly when and where it needed to. During perihelion, when 3I Atlas was behind the Sun, hidden from Earth-based observation, accelerating in ways we can't measure directly but only infer from orbital changes. If you were designing a mission to reach Jupiter's Hill radius and wanted to hide the navigation, the optimal time for course correction is perihelion. Telescopes can't observe through the Sun. Whatever thrust events occurred during that period remain unmeasured except through their effects on the subsequent orbit. And those effects placed 3I Atlas on a trajectory that will, according to the original JPL forecast, arrive at the Lagrange points with precision, suggesting deliberate targeting. Then came NASA's revision. The acceleration model changed from water-based physics to carbon dioxide-based physics, reducing the estimated acceleration magnitude by a factor of 6 and spreading the effect over larger heliocentric distances. The new forecast places 3I Atlas at 53.587 million kilometers from Jupiter, about 85,000 kilometers outside the Hill radius. The coincidence disappears. The targeting becomes near miss rather than direct hit, and institutionally, the extraordinary claim that 3I Atlas might be navigating toward an optimal satellite deployment altitude gets diffused into a less remarkable claim that natural sublimation produced trajectory that almost, but not quite, matches a gravitationally significant boundary. But the revised model contradicts observational evidence. Multiple independent analyses of 3I Atlas's brightness evolution show steep radial dependence near perihelion, far steeper than carbon dioxide sublimation produces. Water ice vaporization creates that kind of steep profile because H2O only becomes active inside about 2 astronomical units from the Sun, ramping up rapidly as temperatures rise, producing the 1/R to the 7.5 power relationship that Zhang and Batoms documented. Carbon dioxide sublimates more gently, starting at 3 astronomical units, or farther, producing shallower dependence around 1/R². The observations support water. The revised model uses CO2. That's not refinement. That's model selection to achieve a predetermined outcome, the elimination of the Hill radius coincidence. And there's precedent for this kind of institutional response to anomalies that threaten paradigms. The history of science is filled with examples where data pointing toward revolutionary conclusions got explained away through increasingly elaborate conventional theories until accumulating evidence made the old paradigm untenable. Stellar parallax, the apparent shift in star positions as Earth orbits the Sun, was predicted by heliocentrism, but not detected until the 1,830 seconds. Because stars are farther than anyone imagined. For centuries, the absence of detectable parallax was used to argue against heliocentrism, with geocentrists claiming that if Earth really orbited the Sun, we'd see stellar positions change. The heliocentric camp responded with the correct but unverifiable claim that stars are simply too distant for parallax to be measurable with available instruments. Eventually, better telescopes vindicated heliocentrism, but for 200 years after Copernicus, the lack of parallax was legitimate evidence against the revolutionary model, explained away by heliocentrists through assumptions about stellar distance that couldn't be confirmed. Continental drift faced similar resistance. Alfred Wegener proposed in 1912 that continents move, drifting across Earth's surface over geological time, based on matching coastlines, fossil distributions, and rock formations on opposite sides of oceans. The theory explained multiple observations elegantly, but geologists rejected it because Wegener couldn't provide a mechanism. How could solid rock continents plow through solid ocean floor? The physics seemed impossible. So, conventional geology clung to static continents, despite accumulating evidence that they had moved, inventing increasingly complex explanations for fossil matches and coastline similarities, until seafloor spreading was discovered in the 1,960 seconds, providing the mechanism and vindicating Wegener decades after his death. We might be watching a similar dynamic now. Observations of 3I Atlas accumulate anomalies. Anti-tail pointing sunward against solar wind pressure. Jets extending millions of kilometers with tight collimation. Mass loss exceeding 10% of minimum estimated mass without nuclear fragmentation. Trajectory aligned within 5 degrees of the ecliptic plane despite interstellar origin. Non-gravitational acceleration during perihelion producing course correction that places the object precisely at Jupiter's Hill radius. Each anomaly individually has potential natural explanations. The anti-tail might result from unusual outgassing geometry. The jets might be sustained by surface area larger than Hubble imaging suggests. The mass loss might be survivable if the nucleus is stronger than typical comets. The ecliptic alignment might be 1 in 500 chance. The Hill radius match might be coincidence. But collectively, the anomalies compound. Multiply the individual probabilities, and the product becomes vanishingly small. A natural object displaying all these characteristics simultaneously requires multiple, unlikely circumstances to align, each one improbable but possible, their combination approaching impossibility. Meanwhile, the technological explanation makes everything straightforward. An interstellar probe designed to survey our solar system would naturally align its trajectory with the ecliptic plane to maximize planetary encounters. It would employ propulsion, producing collimated jets at velocities exceeding thermal sublimation. It would be built from materials strong enough to survive mass loss without fragmenting, and it would navigate toward gravitationally significant locations like the Hill radius to deploy instruments at energetically optimal altitudes. Occam's razor, the principle that simpler explanations are preferable to complex ones, doesn't automatically favor natural over technological. It favors whichever explanation requires fewer independent assumptions to match all observations. And right now, the natural explanation requires assuming unusual outgassing, unusual strength, unlikely trajectory alignment, and coincidental Hill radius targeting. 4 independent unlikelihoods. The technological explanation requires assuming just one thing: that 3I Atlas is a probe. That single assumption explains all anomalies simultaneously, without needing separate unlikely circumstances for each observation. By Occam's standard, technology might actually be simpler than the increasingly baroque natural explanations being constructed to preserve the paradigm that comets are always natural. Part 2. What happens if objects appear around Jupiter after the flyby? Let's game out the scenario where 3I Atlas genuinely is a mothership and does release satellites during the March 16th encounter. What would we see? What would the evidence look like? And how would we distinguish between deployed technology and natural fragmentatio, or captured debris? The answers involve understanding detection capabilities, orbital mechanics, and the specific geometries involved in the Jupiter system during March 2026. First, the detection problem. Jupiter is 780 million kilometers from the Sun during the encounter, roughly 5 times Earth's distance. From Earth's perspective, Jupiter and 3I Atlas will be visible as separate objects in the sky, resolvable with moderate telescopes, but not close enough for detailed imaging of small satellites. The spacecraft in position to observe directly are Juno, NASA's Jupiter orbiter that has been studying the gas giant since 2016, and potentially JUICE, the European Space Agency's Jupiter Icy Moons Explorer, currently en route and scheduled to arrive at Jupiter in 2031, but possibly close enough in 2026 to contribute observations. Additionally, the Psyche spacecraft, launched by NASA in October 2023 to explore a metal-rich asteroid, will be relatively near Jupiter's orbital path in March 2026 and could provide imaging if redirected. Juno's capabilities are relevant here. The spacecraft orbits Jupiter in a highly elliptical trajectory, swooping close to the cloud tops every 53 days, then swinging out to distances exceeding several million kilometers from the planet. The orbit's orientation and timing during March 2026 will determine whether Juno is positioned to observe 3I Atlas's flyby. If Juno happens to be at Apogee, the farthest point in its orbit, during the encounter, it might be tens of millions of kilometers from Jupiter, too far to resolve small objects released by 3I Atlas, but close enough to detect brightness changes or new orbital companions through sensitive instruments. If Juno is at perigee, close to Jupiter, it will be on the wrong side of the planet to observe the 3I Atlas approach directly, but could detect objects released into Jovian orbit by tracking them over subsequent weeks. What would deployment look like? If 3I Atlas releases hardware at the Hill radius, that hardware initially shares the mothership's velocity relative to Jupiter, approximately 65.9 kilometers per second. That's fast, far too fast for gravitational capture by Jupiter. Any object moving at 66 kilometers per second relative to Jupiter at a distance of 53 million kilometers will escape on a hyperbolic trajectory unless it decelerates. The escape velocity from Jupiter's gravitational well at that distance is only 2.2 kilometers per second. The deployed object needs to shed nearly all its kinetic energy relative to Jupiter to achieve capture. That requires propulsion, retro-rockets firing to cancel the excess velocity and drop the object into bound orbit. The energetics are significant. Using the Tsiolkovsky rocket equation, achieving a delta V of 64 kilometers per second requires mass ratio exponential of 64 divided by exhaust velocity. For chemical rockets with exhaust velocity around 4 kilometers per second, the mass ratio is exponential of 16, approximately 9 million to 1. 99.9999% of the object would need to be propellant. That's obviously impractical. But for ion thrusters with exhaust velocities around 40 kilometers per second, the mass ratio is exponential of 1.6, about 5 to 1, still large, but achievable with clever engineering. 80% propellant, 20% payload. An object massing 100 tons could deliver 20 tons into Jupiter orbit after burning 80 tons of propellant to decelerate. Would we see that burn? Absolutely. A thruster producing 64 kilometers per second delta V on a 100-ton mass requires continuous thrust for extended periods, days to weeks depending on the engine's acceleration capability. During that time, the rocket plume would be visible, either as optical emission if using chemical propulsion or as ionized exhaust if using electric drives. Juno's instruments, particularly its ultraviolet spectrograph and visible light camera, would detect the exhaust plume if they're pointed in the right direction. Ground-based telescopes observing Jupiter in March 2026 might also see transient flashes or brightness changes near the planet if deployed objects are firing large thrusters. After deceleration, the captured objects would orbit Jupiter in whatever trajectory their remaining velocity vector provides. Depending on the deployment geometry, they might end up in highly elliptical orbits, in near-circular orbits close to the Hill radius, or in transfer orbits that eventually circularize through additional burns. Tracking these orbits from Earth would be challenging because Jupiter's glare makes detecting faint objects nearby difficult. But Juno could catalog new satellites by imaging Jupiter's vicinity repeatedly and looking for point sources that move against the background stars in ways consistent with Jovian orbit rather than main belt asteroids or background stars. Jupiter already has 95 known moons, most of them small, irregular satellites captured from passing asteroids over billions of years. Adding a few new moons wouldn't be inherently suspicious. The question is whether new objects appear suddenly after 3 eye atlases fly by, objects that weren't present before and whose orbits indicate recent arrival rather than ancient capture. That temporal correlation, new satellites appearing within days or weeks of the interstellar visitor's passage, would be strong evidence of deliberate seeding. Natural capture during a flyby is possible, but extremely unlikely because it requires the captured object to lose kinetic energy through interactions with Jupiter's atmosphere or existing moons. And 3I Atlas is passing too far from Jupiter for atmospheric drag and too fast for gravitational interactions with moons to dissipate enough energy. If we find technological satellites around Jupiter that we didn't place there, the implications are staggering. It means 3I Atlas is indeed a probe, that extraterrestrial intelligence has deployed hardware in our solar system, and that Jupiter is of interest to whoever sent the mothership. But it also raises uncomfortable questions. Why Jupiter instead of Earth? If the visitors are studying habitable environments and technological civilizations, Earth is the obvious target. We have liquid water, oxygen-rich atmosphere, radio transmissions leaking into space for nearly a century. Jupiter has none of those markers. It's a gas giant with no solid surface, crushing atmospheric pressure, and radiation belts intense enough to destroy unshielded electronics within hours. What could make Jupiter more interesting than Earth? One possibility is that the visitors prioritize different criteria. Perhaps they're studying magnetic field generation, and Jupiter's magnetosphere, the strongest in the solar system, is their primary interest. Perhaps they're investigating atmospheric dynamics, and Jupiter's centuries-old storms and banded cloud structures offer natural laboratories. Perhaps they're surveying moon systems, and Jupiter's 95 satellites, including the ice-covered ocean worlds, Europa, Ganymede, and Callisto, represent astrobiologically rich targets. Or perhaps the visitors have already deployed hardware at Earth, Mars, Venus, and other terrestrial planets during earlier flybys, and Jupiter is simply the next destination on a systematic survey of the entire solar system. That last possibility is chilling. If 3I Atlas has been releasing satellites at every planet it passes, if objects are already orbiting Earth undetected because we lack comprehensive space surveillance systems capable of cataloging every piece of debris in cislunar space, then we've been under observation for months without knowing. Our satellites are tracked, yes, known debris is cataloged, but small, stealthy objects designed to avoid detection. Satellites, massing a few hundred kilograms with minimal radar cross-section and no active transmissions, could hide in the clutter. We wouldn't see them unless we were specifically looking. And we haven't been looking because we've assumed all satellites near Earth are either ours or natural debris. This is the nightmare scenario for planetary defense. Not kinetic impactors threatening collision, not biological contamination from sample return missions, but intelligence operating in our vicinity, deploying hardware we can't detect, conducting observations we can't prevent, gathering data for purposes we can't fathom. And our first confirmation coming not from detecting the objects around Earth, where they might already exist, but from detecting them around Jupiter, where Juno happens to be positioned to observe. At that point, the questions shift from, is 3I Atlas technological, to, how long has this been happening, and what do they want? Part 3. The Data War, and what NASA isn't saying publicly. Let's return to the central controversy. NASA's revision of the acceleration model and what that revision reveals about institutional dynamics when confronted with anomalies that don't fit comfortable frameworks. The timeline is revealing. Avi Loeb publishes his analysis of the Hill radius coincidence on November 24th. The article explains the match, calculates the statistical improbability, and proposes that 3I Atlas might be a mothership designed to seed Jupiter with technology. Loeb emails the analysis to David Farnokia at JPL, the scientist maintaining the Horizons ephemeris data. No response. But within 48 hours, the acceleration coefficient, A1, listed on the Horizons website, drops by a factor of 6, from 1.6 times 10 to the -6 to 6.8 times 10 to the -8 astronomical units per day squared. The Perijov forecast changes from 53.445 million kilometers to 53.587 million kilometers. The Hill radius match disappears. NASA has made no public announcement about this revision, no press release explaining the model change, no acknowledgement that earlier forecasts were based on incorrect assumptions. The update simply appears on the JPL Horizons website, accessible to anyone who knows where to look, but invisible to casual observers who aren't tracking these details obsessively. This is not how major revisions to spacecraft trajectories or asteroid orbits are typically handled. When an asteroid's predicted close approach distance changes significantly, NASA issues statements explaining the revised risk assessment and why the earlier forecast was incorrect. When a spacecraft's trajectory needs adjustment, mission planners publish detailed analyses documenting the maneuver requirements and the reasons for the change. But for 3I Atlas, the most widely publicized interstellar visitor in recent memory, the trajectory revision happens silently. Why the silence? One possibility is that the revision is minor from NASA's perspective, a routine update based on improved understanding of the object's outgassing, not worth public communication because it doesn't change any risk assessments or mission plans. 3I Atlas poses no collision threat, regardless of its exact trajectory. The March 2026 Jupiter encounter is scientifically interesting, but doesn't involve any NASA spacecraft making close approach observations that would require trajectory precision. From an institutional standpoint, updating the acceleration model from water-based to CO2-based physics is just normal refinement as new data becomes available. But another possibility is that NASA is deliberately avoiding drawing attention to the Hill radius coincidence because acknowledging it would require addressing Loeb's technological hypothesis. Official statements about 3I Atlas have consistently emphasized the object's conventionality, describing it as a large comet from another star system, displaying behavior consistent with natural sublimation and posing no threat to Earth. The November press conference following the government shutdown reiterated this message. NASA officials stated that 3I Atlas is understood to be a natural object, and that while its size and interstellar origin make it scientifically interesting, nothing about its behavior requires extraordinary explanations. That framing collapses if the Hill radius match is real. A 1 in 26,000 coincidence, enabled by course correction during the only period when observation was impossible, doesn't fit the nothing extraordinary narrative. It demands acknowledgement that something unusual is happening, that the object's trajectory shows precision inconsistent with random gravitational dynamics, and that technological navigation remains a hypothesis worth serious investigation, even if not yet proven. NASA doesn't want to have that conversation. The institutional mandate is planetary defense and space science, not astrobiology or SETI. Acknowledging that an object in Earth's vicinity might be extraterrestrial technology falls outside NASA's comfort zone, inviting congressional scrutiny, public anxiety, and media attention that distracts from the agency's primary missions. So the revision happens quietly. The model changes from water to CO2. The perigove forecast shifts, and the Hill radius match becomes near miss instead of direct hit. Problem solved, anomaly diffused, narrative preserved. Except the revision is based on questionable assumptions, contradicting the observed brightness evolution that multiple independent analyses have documented. And if the revision is wrong, if the actual trajectory does take 3I Atlas to the Hill radius as the original forecast predicted, then NASA's quiet revision will look in retrospect like an attempt to suppress evidence of something the agency wasn't prepared to confront. This is the institutional vulnerability that Loeb has been highlighting throughout his career. Scientific organizations, for all their commitment to objectivity and evidence-based reasoning, are still organizations subject to political pressures, budget constraints, and cultural inertia. When data points toward conclusions that threaten funding, contradict leadership statements, or challenge paradigms the institution has invested decades building, there's tremendous pressure to explain the data away, to find alternative interpretations that preserve the comfortable framework. And in many cases, alternative interpretations are legitimate. Data is ambiguous. Models are approximate. Uncertainty is real. But sometimes, maybe rarely, the uncomfortable interpretation is correct, and distinguishing between legitimate skepticism and motivated dismissal becomes impossible without external review, independent analysis, adversarial collaboration that challenges institutional narratives. Loeb serves that function for 3I Atlas. He's the outside voice saying, "Wait, look at this. The numbers don't add up the way NASA claims. The revised model doesn't fit the brightness data. The original forecast might be more accurate. His analysis isn't perfect. His conclusions might be wrong. But his role in the process is essential, because institutions need external challenges to remain honest. Without someone pointing out that the emperor might be naked, that the model revision might be questionable, that the Hill radius match might be real, NASA could revise away every anomaly without ever confronting the possibility that 3I Atlas is genuinely unusual. And the stakes are high. If we're entering an era where interstellar visitors arrive regularly, where some fraction might be technological, then developing robust protocols for identifying non-natural objects becomes critical. We can't rely on institutional conservatism to protect us from false positives if that same conservatism blinds us to true positives. The cost of false positive, incorrectly identifying a natural object as technological, is embarrassment and wasted resources investigating something that turns out to be mundane. The cost of false negative, incorrectly dismissing a technological object as natural, is missed opportunity for contact, failed detection of intelligence operating in our vicinity, and potential vulnerability if the visitors have purposes incompatible with human interests. Balancing those costs requires humility, recognition that our current understanding might be incomplete, that anomalies deserve investigation proportional to their significance, regardless of whether they fit comfortable frameworks. And it requires transparency, open data, public analysis, willingness to engage with critics, even when criticism is uncomfortable. NASA's quiet revision of the 3I Atlas acceleration model fails that standard. The change should have been announced, explained, documented with reasoning, showing why CO2 physics is more appropriate than water physics, despite the brightness observations suggesting otherwise. Instead, the revision appeared silently, leaving external analysts like Loeb to discover it and point out the implications. Part 4. What December and March will reveal. In 3 weeks, 3I Atlas makes its closest approach to Earth. In 4 months, it reaches Jupiter. Those 2 encounters will provide definitive data, resolving the ambiguities that currently make both natural and technological interpretations defensible. Let's walk through what each observation opportunity will show and how the evidence will force conclusions. December 19th, 269 million kilometers from Earth. Hubble Space Telescope will image the nucleus at resolution sufficient to detect surface features down to a few hundred meters if they exist. Geometric structures, flat panels, cylindrical components, arrangements too regular to result from natural erosion would be visible. Webb Space Telescope will map thermal emissions in infrared, measuring temperature distributions across the nucleus. Hotspots warmer than solar heating alone can explain would indicate internal heat sources, power systems generating thermal signatures. Ground-based spectroscopy will measure chemical compositions in the jets, identifying volatiles and their relative abundances. Water, CO2, carbon monoxide, methane, ammonia, all produce characteristic emission lines. The ratios reveal whether the composition matches solar system comets or displays exotic chemistry. And Doppler measurements will determine jet velocities with precision down to a few meters per second. Thermal sublimation produces velocities around 400 to 600 meters per second. Chemical propulsion produces 3,000 to 5,000 meters per second. Ion propulsion exceeds 30,000 meters per second. The velocity distinguishes mechanisms unambiguously. If December observations show natural composition, thermal velocities, no geometric structures, and temperature distributions consistent with solar heating, then the natural interpretation gains strength. The object behaves like a comet, looks like a comet, and probably is a comet despite the statistical anomalies. Those anomalies become coincidences, unlikely but not impossible, the kinds of things that happen occasionally in a large enough sample space. But if December observations show anomalous features, high jet velocities, exotic chemistry, or unexplained thermal emissions, then the technological interpretation becomes unavoidable. You can't explain velocities 10 times higher than thermal physics allows through natural processes. You can't explain geometric surface structures through erosion. You can't explain internal heat sources without power systems. Each anomaly independently might have exotic natural explanations, unusual ice compositions, peculiar outgassing geometries, residual formation energy. But collectively, they point toward engineering. Then comes March 16th, the Jupiter encounter. The perigove distance will be measured precisely through astrometry, tracking 3I Atlas's position against background stars as it passes the gas giant. If the distance matches JPL's revised forecast of 53.587 million kilometers, then the CO2 sublimation model is vindicated, and the original Hill radius match was modeling artifact. NASA's revision is justified. The coincidence was never real. If the distance matches the original forecast of 53.445 million kilometers, landing within 60,000 kilometers of the Hill radius, then Loeb's analysis is vindicated. The coincidence is real. Course correction during perihelion placed the object precisely at the gravitational boundary where satellite deployment is optimal, and the probability of that occurring naturally drops below any reasonable threshold for dismissing it as chance. And if objects appear around Jupiter after the flyby, if Juno detects new satellites in Jovian orbit that weren't present before, satellites whose appearance correlates temporally with 3I Atlas's passage, then speculation transforms into certainty. We have confirmation of deployed technology, evidence that extraterrestrial intelligence is operating in our solar system, and recognition that the visitors possess capabilities far beyond current human achievement. At that point, the questions shift from whether 3I Atlas is natural to what its mission entails, where it came from, and what it intends to do next. The stakes could not be higher. March 2026 might be remembered as the moment when humanity confirmed it is not alone, when paradigms about cosmic solitude shattered, when the universe revealed itself as populated, and our solar system as subject to visitation by intelligences older and more advanced than ourselves. Or it might be remembered as the moment when careful observation showed that anomalies have natural explanations, when skepticism was vindicated, when the extraordinary interpretation proved unnecessary despite initial appearances. We don't know yet which history we're living through. The data is ambiguous. The models disagree. The experts are divided. And that's exactly when scientific integrity matters most, when evidence could go either way, and the choice of interpretations determines which future becomes real. Do we follow NASA's revised model and conclude that 3I Atlas will miss the Hill radius, that the coincidence was artifact, that nothing extraordinary is happening? Or do we follow Loeb's analysis and conclude that the revision is inadequate, that the original forecast was more accurate, that 3I Atlas is targeting the Hill radius with precision suggesting navigation? The answer will emerge through observation. March will force clarity. And regardless of which interpretation proves correct, the process of getting there reveals how science responds to anomalies that challenge comfortable assumptions. Are we capable of genuine openness to evidence regardless of implications? Or are we too constrained by paradigms, too invested in comfortable frameworks, too resistant to conclusions that threaten worldviews we've spent lifetimes building? The answer to that question defines not just this era of astronomy, but the nature of scientific inquiry itself. Thank you for following this investigation, for thinking critically about what the data means, for refusing to accept easy answers when the observations demand deeper analysis. The sleepy observer exists to explore these boundaries, to examine the mysteries that mainstream institutions sometimes overlook, to ask whether the universe is what we think it is, or something far stranger and more wondrous. Subscribe so you don't miss what happens in March. Comment with your thoughts on whether NASA's revision is legitimate refinement or motivated dismissal. And remember that we're all watching this unfold together. witnessing either the beginning of a new understanding of our place in the cosmos or another chapter in the long story of anomalies that ultimately proved explicable through conventional physics. Good night, and clear skies.